Hello. So, in this video, we're going to be tackling implicit functions. So we're going to start with sort of a reminder, a refresh of implicit functions that hopefully you've seen before, like in pre-calc or whatever. But we're going to sort of do a quick review of what an implicit function is, and sort of importantly, the notation that's involved, because it turns out that's going to be kind of important when we talk about the calculus aspects of it. And then the sort of second half of this video, we're going to be talking about how to take derivatives of implicitly defined functions. Okay, so to start off, we're used to functions like normal functions being defined in a way that makes the output pretty obvious, right? So we have this, for example, y equals 3x squared minus 12. The x is the input, so that's the independent variable. The y is the output, so that's the dependent variable. And this is the sort of classic explicitly defined function we all know and some of us love more than others. But as we also know, hopefully, implicitly defined functions, these are also a thing. And in particular, we can have functions where, as we can see, right, we still have our same variables, but sort of importantly here, the dependent variable, the y, that thing is on both sides and may not even be solved sort of nicely on either one, right? On one side here, it's sort of matched in with the x, and on the other side, it has this, square attached. And we still have the input, right? So it's not just the dependent variable, which is the output. We also have that independent variable, the input, mixed in with that as well, okay? So we have this explicit versus implicitly defined functions. So the thing is that sort of from a normal function standpoint, these things are pretty close, even though they don't necessarily look it. So implicitly defined functions, they're essentially the same kind of thing as explicitly defined functions in most ways. One notable difference, the dependent variable is usually not isolated. So there's something going on with the dependent variable. For example, you could have the dependent variable, right, on one side and maybe have a function of it, but like this is an example of what would be considered an explicit function, right? Because we have just the dependent variable on one side and it's just by itself. It's y equals stuff. In contrast, for an implicitly defined function, we could also still have y equals stuff, right? We could still have it look like it's sort of solved for, but it's not, right? Because we have this y's on this other side as well, okay? So implicitly defined functions are functions that are not sort of, don't have that dependent piece isolated. So this is where sort of our normal notation can hurt us. So we write the dependent variable as just a variable, right? So we write it as y, for example. But in reality, what makes it implicit, what makes that function an implicitly defined function, and really inherently what makes a dependent variable dependent, is that it depends on something. So in particular, our dependent variable is really a function of an input, right? The idea is that to get a y value, you're supposed to plug in an x value. This can sort of be very confusing because our sort of arguably a little lazy way of writing this notation can end up with two things that look exactly the same, but are very importantly different. So for example, we could have an implicitly defined expression, right? We could have this where y is a function of x, and so these things are sort of intermixed and it's implicitly defined. Or we could have that exact same expression, but it is now explicitly defined as a multivariable function, which is to say that x and y in this case would both be inputs and there'd be some other variable like z that would be the output. So for any of you moving on past this course for calculus, so if you are going to be taking one of the sort of other calculus parts like calculus 2 for engineering, or if you go into the next survey 2 of calculus, you will encounter this sort of difference, and it can be confusing because they look exactly the same, but they are very different things that you have to deal with differently. For this reason, it's actually useful to write when you have an implicitly defined function, right? When you have y that is the output, the dependent variable, and it depends on the input, the x, it can be useful to write it as y of x, right? This is just to remind us that, yeah, y is some value, right? It's some variable, but it's not something that I'm putting in. It depends on this x value, okay? So it's a way of making the implicit nature explicit, which I realize is kind of a nice juxtaposition of that there. So it can be helpful to write this, but remember that like these are letters, right? Obviously, y is just a letter we choose for sort of ease and familiarity, but having something of x should look pretty familiar even from a long time ago. So in particular, we can think of this as just an f of x, right? There's nothing special about the letter y versus the letter f in this context. And we already know how to do derivatives of f of x, right? We just have this f prime of x, right? So this is sort of leading us down the rabbit hole of how we actually are going to tackle this from a calculus standpoint. So when we have implicitly defined functions, the sort of rule of thumb is that we can take the derivative as normal, but then we're going to need to apply some sort of chain rule effect. Basically, we need to keep track of the fact that where the derivative is being applied to the dependent variable, we need to sort of make note of that fact, okay? So I'm gonna sort of go through an example here of doing sort of a derivative process on an implicitly defined function, but I'm going to show you sort of the y notation that is usually shown when we do this sort of topic, and what you'll probably run into if you look this up anywhere else, versus sort of an f of x version that will hopefully look more familiar from a sort of more sort of explicit point of view, okay? So let's take a look here. Let's say that we want to do the function, right? We want to take a derivative of the function y squared equals 3xy. So as we can see in this column, right, I'm going to have the y version of what's happening. In this column, I'm going to show the f version of what's happening. And here I'm just going to basically tell you what's happening in each line. So I would actually recommend sort of looking at the f version first, and then sort of seeing how it compares to the y version. And the sort of idea here is that you will hopefully see that doing it with just the y notation is much more compact and much sort of visually nicer, but it's a little harder to follow what's happening compared to the f of x version. So this f of x version will, again, hopefully sort of be a good way of starting this. So when you're doing your own work, it might be helpful to do it sort of by converting a y to an f of x and doing it this way. But eventually, the goal is to move into doing it sort of with this y version, okay? So that's the sort of overall sort of idea of what we're doing here. So let's move forward. So first thing we're going to do is we're going to take the derivative, right? So we have this d over dx. This is the derivative action, and all I'm saying is, okay, I'm going to take the derivative of d of dx. I'm going to take the derivative of y squared, and I have to do it to both sides, so I'm also taking the derivative of 3xy. And over here, same deal, but now instead of y, I have f of x. So f of x squared and 3 times x times f of x, right? Okay, so now the next step, I'm going to do just the left side. So here, right, I have the derivative of y squared, derivative of f of x squared. I know that if I take the derivative of something squared, it's 2 times that thing, but then I have to apply the chain rule, right? Then I have to multiply by whatever the derivative of that thing is. So here, I'm doing derivative of f of x squared, so it's 2 times that thing, 2 times f of x, times the derivative of that thing, times the derivative of f of x. Same with the y, right? I had y squared, so it's 2 times y, times the derivative of that thing, y. Okay? But the derivative of something that is just a function, right, is just, we use that prime notation. So the derivative of f is just f prime. So I'm going to do the same thing with y. The derivative of y is y prime. So it's common to see this sort of y prime notation, meaning that this is sort of interchangeable with f prime, and it's just telling me that y is the sort of dependent variable that I'm dealing with. Okay. So next up, I have to do the right-hand side, but the right-hand side is a product, right? I have 3 times x times f of x. So I need to apply a product rule, and I'm going to apply that by doing 3x as my first term and f of x as my second term, right? So the product rule says, okay, take the derivative of the first thing times just the second thing, plus the first thing times the derivative of the second thing, right? So that's exactly what I have here. Derivative of 3x times just f of x plus 3x times the derivative of f of x. And again, same over here, derivative of 3x times y, that second thing, plus 3x times the derivative of y. Derivative of 3x is just 3, right? So this derivative of 3x becomes 3, and this derivative of 3x becomes 3. And again, the derivative of a dependent variable or derivative of a function is just that prime notation. So derivative of f of x is f prime of x versus derivative of y is f prime of y, okay? So this is the process of doing the implicit derivative step, okay? So in particular, the dependent variable y, you can really think of this as a disguised version of the function notation, right? So the y is really just a disguised form of f of x. And similarly then, because they're basically the same, y prime really means f prime, okay? Now, we've done the calculus part, but there's one more thing to do with implicit derivatives, which is that we've now got this y prime here, but our goal is to find the derivative, which means our goal is to have something that looks like, or in the f terms here, we have f prime, and our goal is to have something that looks like f prime equals stuff, or y prime equals stuff. And that's not what we have, okay? So here, then, we sort of have a little bit of follow-up, which isn't calculus, it's pre-calculus, but it's still pretty important, which is that we're going to try to solve for y prime. This is going to be our goal, right? So this is just from that previous thing we did. We took the derivative of y squared equals derivative of 3xy, and we eventually got it down to this y prime notation, this part here. So to keep going, I want to solve for y prime. So the first thing I'm going to do is try to get all my y prime stuff on one side and all of my non-y prime related stuff, in this case 3y, on the other side, right? So I have all of these terms on one side have a y prime in them, and everything on this side, there is no y prime to be found. Then I'm going to factor out the y prime on both sides. So I factored out a y prime here, and then divide by basically the stuff that is attached to y prime. So I have this 2y minus 3x, so I divide it over to get sort of this y prime isolated, okay? Now, it's sort of worth a note here that we started with an implicitly defined function, and so it's sort of natural that we would end with an implicitly defined function, right? So it's not a bad thing, and it's not even surprising that we have y's and x's on this side, right? The y prime equals, and we have sort of a nice, well, not maybe nice, but a relatively okay implicitly defined sort of piece there. That's totally normal. Don't have to worry about that, okay? All right, deep breath. So we saw how sort of the explicitly and implicitly, how those functions, these kinds of functions sort of interact in terms of like, where are they sort of similar or not similar? We saw the function bit with the notation and how that is sort of important. The next thing that we're going to sort of tackle is trying to figure out when do we need implicitly defined stuff? Like, how do I know that if I'm taking a derivative, how do I know that y deserves a y prime? Why is it that x isn't the thing that deserves an x prime, which I know you're probably thinking like, that's a thing. Sadly, yes, that's a thing. So that's what the next part of the video is going to be. But before we jump into that, sort of, we got a lot of stuff here to digest. So just take a minute, take a breath, make sure you sort of followed along and are okay with what we've done. And then we will dive into that part. Okay. Welcome back. All right. So moving forward now, our goal is to know sort of how to know when a term is implicitly defined. So our sort of goal now is to say, okay, when do you include something like y prime or not? How do I know if that is going to be a thing? How do I know which letters are involved? If I'm doing some like function of t versus function of x versus function of q or something, like how do I know, right? So the good news is that this is entirely encapsulated in the notation. So there's sort of a hidden part about notation that we haven't really discussed because it doesn't necessarily make sense until we are talking about implicitly defined things. And to sort of see that, again, let's sort of do a nice toy example. We have this thing here. We're used to this thing, sort of thinking of this thing as just the derivative, right? We think of this d over dx as the derivative of, and then this inside piece, x plus y, right? This is what we're normally thinking of. But it turns out that there's a little bit more that this first little bit is telling us. So this little bit, this d over dx, is what is mathematically called an operator. This is not a thing that we're going to need to worry about in this class, because that's sort of what makes an operator or not is a surprisingly advanced term. If this is something that you want to know more about, I would sort of recommend asking your lecturer or whatever. But if this is something you turn out to want to pursue more, this is something that's covered in advanced calculus. That's the name of the course. So regardless, the derivative operator, from our perspective, the thing that we care about, this tells us when we take a derivative, so it tells us to take a derivative, but it also tells us with respect to what. And so that is the key part that we're really going to care about. So in particular, when we have this d over dx, there's actually more going on here than is sort of immediately apparent. And in particular, the variable down here, this x, this is what is with respect to. So if we see this piece here, this operator, d over dx, we would say take a derivative with respect to x. That's the sort of correct full sentence that this is telling us, or phrase, I guess. And in particular, what that's saying is that this thing is assuming or treating x as the independent variable, okay? But that also means that any other variable that doesn't match that, so if you have any other letters, in your form, right, in your function and expression, whatever you're dealing with, those things are sort of automatically treated as dependent variables that depend on something, okay? That is a little vague because explicitly defining what we mean by depend on something, again, drifts well outside the scope of this course. But for the sake of what we sort of care about, we are going to assume that the thing that those letters depend on is an x. Okay, so let me sort of give, again, another sort of concrete version of this thing. So we saw, right, I sort of introduced this toy example here, this derivative, right, this saying take a derivative with respect to x of x plus y. So to do that, right, I can apply my sum formula, right? I can break this up as the derivative of x plus the derivative of y. But again, to hammer home, this really says take the derivative with respect to x of x plus take the derivative with respect to x of y, right? Since the pieces match in that first part, right, this d over dx of x, so since those two things match, I'm taking the derivative with respect to x of x. That tells me that I don't have to worry about any sort of prime notation. I just move along happily, right? So the derivative of x is just 1. That's it. I'm done with that term. Now, the other one doesn't match, right? So in particular, I'm taking it with respect to x of y, and these are different letters. This also tells me what to do, which just means I have a little bit more to do. So what that means is that I start by sort of just treating whatever's in here, whatever that letter is, as if it were an x in terms of taking the derivative. So if I'm looking at this, right, with respect to x of y, I pretend for a second that's an x, so that means it would be a 1, just like it was before. But once I'm done taking the derivative, which, like here, it's just y, but if this were, involving product rules and like quotients and stuff, there might be all kinds of things involved. Once I'm done taking the derivative, I then need to apply the chain rule, which is really just saying, okay, I took the derivative of a thing of the form y to the 1, which means I drop the 1 down in front, subtract 1 from the power, that gets me 1 times y to the 0, which is just 1. Then the chain rule says, okay, times the derivative of the thing inside. The thing inside is a letter that doesn't match. So again, since it doesn't match, right, x and y are different, I have this times y prime from that chain rule, okay? And then finally, I just simplify. So I'm down to 1 plus y prime. Now to be clear, in your own work, you don't have to show, like, you don't have to have this 1 times y prime bit. I'm just trying to be very sort of explicit, showing all of the steps bit by bit to show what's happening here. And likewise, how this is done, this is a nice example, right? I'm doing this because we're introducing the idea, but I very much encourage you to watch the example videos where there are going to be more complicated expressions to take derivatives of and see how this all works out, okay? But the general rule of thumb, right, the takeaway from that is that if the variable in the bottom of your operator, in the bottom of this d over d whatever, right, that variable, like u here or x or q or y or whatever it is that you're using, if it matches the variable, right, if it's the same as what you're taking the derivative of, then you don't have any chain rule, there's no prime terms, everything works great. If they don't match, then you should end up with some sort of chain rule giving you a prime version of whatever the variable is that you're taking the derivative of, multiplying whatever you got out, okay? I realize this is one of those things where, like, trying to explain it with words is inevitably confusing. This is much easier to just see some examples, so I'm going to go through examples where I'm going to take the derivative of a bunch of different variables, but show it with respect to different variables each time. So for example, looking at this, right? This is saying, okay, take the derivative with respect to a of a. Well, these things match, so I just get 1, right? Take the derivative with respect to a of b, they don't match, so I get b prime, right? I really get 1 times b prime, but you don't have to sort of have that middle step. Similarly, the derivative with respect to a of c is c prime, because again, they don't match, right? Derivative with respect to a of x, x prime, right? So x isn't always the thing that doesn't have a prime, right? It's not always the case that if you're taking a derivative of an x, it's just 1. That's often the case because we are often using x as the default independent variable, and thus we are often just taking a derivative with respect to x, but it's important to know when that matters and when it doesn't, right? And like I know I'm beating a dead horse here, but like this is the thing, is that you know based on that letter in the bottom here, right? So just looking at a couple more things, and I'm not going to go through like all of these super carefully, but again, right, if I'm doing now instead of with respect to a every time, I'm doing with respect to b every time, then instead of the derivative of a being 1, now it's a prime, and instead of b being b prime, now it's 1 because they match, right? But these still don't match, so they still get c prime and x prime. Likewise, if I did it with respect to c, the a and b don't match, so I get a prime and b prime. The c does match, so I get 1. X doesn't match, so I get x prime, right? And sort of last but not least, if I am doing with respect to x, then I'm going to get a prime, b prime, and c prime, but now those x's match, and so I get 1, right? So all of this comes down to the notation sort of straight up tells you what's going on. And it says, okay, if it matches, then no primes, you're fine. If it doesn't match, then you need that prime left over, okay? All right, so this is a bit of a long video, but what did we do? So we talked about implicit differentiation sort of as a tool, and really how it's nothing more than the chain rule, and recognizing that sometimes we use these dependent variables like a y in lieu of that sort of function notation like f of x, right? So the whole thing with an implicitly defined function, right, an implicitly defined single variable function versus, say, an explicitly defined multivariable function is that it's really like we write y, but we really mean y of x, right? And so instead of doing it like this, because it sort of takes a lot more writing and is much longer and sometimes harder to read, we sort of simplify it down to a y and use y prime, but it's really the same thing, So to that end, right, big takeaway here, don't let the notation trip you up. If you want to keep track of what the derivative is with respect to, so like when you're doing the derivative, it's important to make note of what it's with respect to so that when you run into variables that do or don't match, you know whether it takes a prime or doesn't take a prime, right? And finally, when those letters don't match up, right, you just need that sort of leftover prime notation, and that's a consequence of the chain rule. And I realize sort of it maybe wasn't as obvious because I'm trying to use relatively simple functions here, but thinking of it in terms of the chain rule is very helpful when we get much more complicated expressions. And in fact, you can sort of see that if you go back and check the first sort of big table that we did when we did that y squared equals 3xy, you can see when y prime showed up. It wasn't sort of like treat all of the 3xy as a thing of x, apply the product rule all the way through, and then tack on a y prime. The y prime showed up as a result of when you were taking the derivative of the y piece. And so sort of attaching it to the idea of the chain rule tells you exactly when in the process that shows up, okay? So in particular, eventually with the chain rule, you end up with something that looks like d over whatever, so this is with respect to x in this case, of y. We can just sort of replace that with y prime, okay? So that is that.